summation of number of moles of product into entropy of product minus summation of number of moles of reactant into entropy of reactant. So all those entropy data will be given to you, and number of moles of product and reactant means I am considering, actually I am telling you, you have to refer to the stoichiometric coefficient of the reactant and product from the balance given reaction, right? And you must check whether the reaction is balanced or not, right? Now the thing is, here I am writing where NR is number of moles of reactant, R for reactant, and this one is number of moles of product. SR is basically entropy of reactant, and SP is entropy of the product. Now for this particular reaction, if at all I have to find out, so I'll be writing deltas for this reaction. For this given reaction, I'm telling you, that will be entropy, or is number of moles of C into entropy of C plus D into entropy of D minus A into entropy of A plus B into entropy of B. Simple. Is there any issue understanding this? Now sometimes examiner may give you standard entropy data, that's absolutely fine. Only thing is, at that time you will be calculating delta as under standard condition. Just be careful there. If they are giving you standard data for entropy, that means all the reactants and products are present in their standard state, and they are giving you basically the entropy value. So basically then you can calculate the delta's reaction under standard condition. Please finish writing it, then I'll give you one particular question based on this. Once we are done, let me know. Okay, done. Now let us go to a question part. Find deltas for the given reaction, and the reaction is N2 gas plus O2 gas, giving you twice of NO2 in the gaseous form. I am writing down the question here. Given entropy of N2 is 180 joule per mole Kelvin, entropy of O2 220 joule per mole Kelvin, entropy of NO2 is 240 joule per mole Kelvin. Find it out, everyone. Find out the answer and let me know. Arey Manas, do not be in hurry, very beta. See whether reaction is balanced or not. Hanudeep has correctly calculated it. Those who are getting 80, please verify whether the reaction is balanced or not. Only one person has given correct answer. In fact, now 3. Likita, is it positive or negative, beta? Value is same. Value is correct. The thing is, I didn't give you a balanced reaction, no? You need to check whether it is balanced or not. People are getting wonderful answer, no? Minus 240, minus 260. How? Now the thing is, delta is for the reaction. You'll be finding out by 2 into entropy of NO2 minus 2 into entropy of O2 plus entropy of N2. So here you will be getting 2 into, I have given you 240 as a value, minus entropy of O2 is 220, plus entropy of N2 is 180. So here you will be getting basically 480 minus 440 minus 180. So basically you will be getting 40 from here and ultimately minus 140 straight away. Joule per mole Kelvin. There's no doubt about it. So variety of answers I am getting. Please verify where you went wrong. First thing is you didn't check whether the reaction is balanced or not. And if at all you are getting some other answer other than minus 140, so maybe you have not substituted the value of the entropy at the correct places. So these are the general mistake. And the third thing is again some addition, subtraction, you have done some mistake. Please avoid these common mistakes. Okay. I hope it is clear now. Those who are getting wrong answer, identified your mistake. Now let us go further for third law of thermodynamics. And this is a very simple law, right? I'm writing the statement here, then we'll try to understand. So we can write down for a pure, perfectly crystalline solid, perfectly crystalline solid, entropy is 0, entropy is 0 at absolute 0 temperature. At absolute 0 temperature, that is 0 Kelvin. Now what is the meaning? It is very simple here, that when I talk about 0 Kelvin, it is the lowest possible temperature, right? Lowest possible temperature means at this temperature, all the molecular motions stop, okay? Nothing is moving from their place. Now when I talk about pure solid, that means there is no impurity there, right? So there is no scope of entropy as such. Now the thing is, when you are having crystalline solid, right? Crystalline solid means there is regular arrangement of the atoms and ions of solid which are present in that crystalline solid. There is a regular arrangement. Now you club these two scenarios together. That means you are having perfectly pure crystalline solid. That means all the atoms and ions which are there is a regular arrangement. 0 Kelvin means nothing is moving from their places. That means there is no randomness, there is no disorderness there. So that's the reason we say that entropy for a pure, perfectly crystalline solid is 0 at absolute 0 temperature. Right? So that's all is your third law, and you should understand that basically according to like this third law will be used for calculating the absolute entropy values. In the previous question I have given entropy values of N2, O2, NO2. So using this third law of thermodynamics we'll be actually finding it out. So you must be aware about what is the application part of it and what does this law states. So I hope this is very clear to you. Now let us proceed towards the next topic here, which is Gibbs energy, or else Gibbs free energy, Gibbs free energy, and the symbol for this is G. Now let us try to understand why even people thought that kind of G should be introduced, and you already know that basically G is a criteria of spontaneity, right? Now let us try to understand this part. When I say spontaneous reaction or a spontaneous process, I'm actually referring to those processes which happen on their own, right? You are not doing anything, you are not bringing any external agency or as any external help from outside to make them happen. They will happen on their own, right? Now the thing is, if you see waterfall, water always falls from a greater height to a lower height, right? And when it is falling from greater height to lower height, at greater height potential energy is more, at lower height potential energy is less. So scientists observed this phenomena. They said when water, or is this falling of water is a natural process, they observed that water is falling from higher potential energy to lower potential energy, or else where the energy is decreasing. So they tried to apply the same thing on basically chemical reaction. Now, so they actually said that in all those reactions, or else all those reactions in which while converting reactant to product, if the energy is getting decreased, then those reactions will happen on their own. That means those reactions are spontaneous. That means according to them, all those reaction, all those exothermic reaction, because when you're converting reactant to product, only in exothermic reaction, energy will be liberated, energy is getting reduced. So they actually gave a conclusion that all those exothermic reactions are actually spontaneous reaction that are happening on their own. But the problem was there were certain endothermic reactions also which were happening on their own. For example, if you take simplest example as ice cube, if you take ice cube in your palm, does it melt or not? On its own? Do you need to do anything there? No. You are not taking help of any external agency there. It is happening on its own. And you start feeling cool. Reason being, that particular ice cube is absorbing the heat from your palm. That is an indication it is an endothermic reaction. So the thing is, certain endothermic reaction also happen on its own. Similarly, when they took ammonium nitrate, right, and they dissolved it in water, so the beaker seemed cool. Reason being, again, the solution, or as when you try to dissolve ammonium nitrate in water, it is an endothermic reaction. That's the reason you start feeling cool, because it is taking the heat from your palm, right? So the thing is, then they cannot simply say that, they cannot conclude that delta H negative, then only it is spontaneous. So delta H negative could be one of the criteria, but not the only criteria. Okay. Now they went on to then second law. According to second law of thermodynamics, they say that any natural process, any irreversible process, any basically kind of spontaneous process that happens in a direction where entropy of the universe increases. And entropy of the universe increases means what? Delta S universe should be greater than 0, right? And when I'm saying delta S universe greater than 0, that means in that expression of delta S universe, do I write down delta S system plus delta S surrounding also? Now for you to calculate entropy change in the system, it is easy, because system parameters you can easily identify. But when it comes to surrounding, right? So for the surrounding, it was difficult to find out the parameters accurately. So again, what happened? Scientists were stuck up. Now the thing is, they wanted to reduce their dependency for dependency on the surrounding parameters for predicting the spontaneity of any process or reaction. So for that reason, actually, they have gone for introducing one more variable, or else one more parameter, that is Gibbs energy, which will be depending only on the system parameters, and based on that you will be able to predict whether a particular process or reaction is basically spontaneous or non-spontaneous. Are we able to understand or not? So for spontaneity, for predicting the spontaneity of a particular process or reaction accurately based upon system parameters only, your Gibbs energy was given. Now let us try to see that mathematically also. So I am writing here, for a spontaneous process, delta S universe should be greater than 0. Let us mark this as 1. Now the thing is, I can always write down delta S universe as delta system plus delta surrounding, that is greater than 0. Now, do you recall that delta surrounding I can always write down as Q surrounding upon T, or else I can write down it as minus Q system upon T. So I can easily write down delta system minus Q system upon T. This is greater than 0. Now let us say I am applying the condition that at constant temperature and pressure, so heat exchange at constant pressure will be actually what? Delta H. So I'll be able to write down this as delta S system minus delta H system upon temperature. This is greater than 0. So let us say this is equation number 2. So are you able to see I have replaced delta S universe only by this particular term? So I can easily compare these two also. So I can write down here delta S universe equal to delta S system minus delta H system upon T. And if I further simplify this, this will become T delta S universe, that is equal to T delta S system minus of delta H system. Let us mark this as equation number 3. Okay. Now I told you that they have introduced one parameter or one variable which was basically Gibbs energy, and whose formula is G is equal to H minus Ts, where H is enthalpy, S is entropy, T is temperature. These variables or these particular parameters, they carry their usual meaning. This Gibbs energy is basically a state function. So when I say it is a state function, it only depends upon initial and final state. It does not depend upon what is the path which the system is following to change the state, right? And it is also an extensive property. Now, do you recall that where you have utilized the extensive property nature of this G, in which chapter? You have already studied that. Where, in which chapter basically you have utilized the extensive property of this G? In which chapter? Can you tell me the name of the chapter? Yes, very good. That is electrochemistry. Now in electrochemistry, you might have calculated electrode potential of one of the half cell using the electrode potential of two half cell using this only, right? Good. It's very good that every one of you remember. Good. Now the thing is, let us say this is equation number 4. I can write down this as delta G system equal to delta H system minus T into delta S system. Let us say this is equation number 5. Now I'm going to compare third and fifth equation. So if at all I now multiply fifth equation by minus throughout, so will it become minus delta G system? Will this become minus delta H system? Will this become plus T delta system? So doesn't it seem like the right hand side of the fifth equation and third equation has become same? So I'll be able to write down here from equation number 3 and 5. What we are going to have is minus delta G system, that is equal to actually T delta S universe. I am simply comparing 3 and 5, right? Now let us draw an important conclusion here from the equation which I have just written. So suppose if I say that if delta G system is less than 0, less than 0 means it is negative. Negative will become positive. Temperature is always a positive value in Kelvin. So will you be getting delta S universe greater than 0? And what does delta S universe greater than 0 tell you? Is it spontaneous or non-spontaneous? Write it on that chat box and let me know. Delta S universe will be greater than 0. Are you able to understand? This is negative, positive divided by temperature, which is also a positive term. So you will be having delta S universe greater than 0. What does it imply? Process spontaneous, non-spontaneous? It is spontaneous, because we have learned in case of second law of thermodynamics that any process happens in that direction where your entropy of the universe is increasing. And in fact, I have written heading also for a spontaneous process, delta S universe should be greater than 0, right? Good. So the thing is here, process is spontaneous. Similarly, if at all I write down now, if delta G system is greater than 0, that means it is positive. So positive negative will become negative and delta S universe will be negative. So delta S universe negative means what? Now the process is non-spontaneous in the forward direction. Whenever I say a process, that means I am talking about a particular process or a reaction which is happening in the forward direction. So in the forward direction it is not spontaneous, in the backward direction it could be. It is, right? So the process is non-spontaneous. Process is non-spontaneous. Now, and the last condition here, which is if delta G system is equal to 0, then delta S universe will become what? Equal to 0. And are you able to recall that when I taught you basically second law of thermodynamics, we have written delta S universe will become equal to 0 for a reversible process, and we know that in a reversible process, system and surrounding, they're always in equilibrium with each other. So I'll be writing here, process is at equilibrium. Process is at equilibrium. So the thing is, now what are the important things which you need to see here is, now this was only for your understanding, right? Now actual criteria has become delta G. So if delta G is less than 0, process is spontaneous. Delta G greater than 0, process is non-spontaneous. If it is 0, it is equilibrium. So now the thing is, we have reduced our dependency on the surrounding parameter for predicting the spontaneity, and we are depending only on delta G, which is going to be calculated based upon system parameters. So by introducing Gibbs energy, dependency of, kind of expressing your spontaneity based upon surrounding is reduced. Are we able to understand this, right? So please write this down, then we'll proceed further. So ultimately from this entire, kind of derivation, what you should be careful about, or what are the important conclusion? First one is you should know that what is that Gibbs energy, what is the formula of it? G is equal to H minus Ts. Second thing is formula is delta G system is equal to delta H system minus T delta S system. Sometimes system will not be written, then also it is understood that delta G is equal to delta H minus T delta S. It is referring to a system. Then the next thing is delta G less than 0, spontaneous. Delta G greater than 0, non-spontaneous. Delta G equal to 0, equilibrium. So these are the important points which you must remember from this derivation which we have done. I hope it is clear. Everybody has finished writing here. Let me know if we have finished writing, then I'll proceed further. Is there anyone who is yet to write this? Only one person is saying done. Anybody still has to write? Acha, people have written, then so good. Well and good. Okay. Okay, then to fine. Then I'll move on to the next one. Now we are going to write down predicting. Application part only we are going to see. Predicting spontaneity of a reaction or process. Now the thing is, we are going to basically make a table here, and that table is important. Delta G is equal to delta H minus T delta S. So I'm going to write down here sign of delta H. 4 columns you make, sign of, simple table, but the thing is still sign of delta S, sign of delta G, and the remarks or conclusion. This table is important because somewhere direct question could be asked. One case we are going to see. Suppose this I have taken as positive, this as negative. Examiner may not mention positive, negative. You must understand positive means delta H is greater than 0. Negative means delta S is less than 0. Right? Now your basic equation remains the same, which is delta G is equal to delta H minus T delta S. So if at all I write down here delta G is equal to delta H minus T delta S, this is positive, delta S is negative, negative will become positive. So ultimately my reaction turns into delta H is equal to T delta S, right? Now the thing is, every time I am dealing with the temperature which are positive on the Kelvin scale, I am not dealing with the negative temperatures here, right? We are not performing reactions or the processes there. Now the thing is here, if at all you see this one, whatever temperature you take, what will be the sign of delta G here? What will be the sign of delta G? Will it be positive? Positive sign means what? Delta G is greater than 0. And if delta G is greater than 0, does it tell you it is going to be non-spontaneous? So this particular thing is non-spontaneous at all temperature. Good. Majority of you answered correctly. Very good. So you can write down this one as non-spontaneous at all temperatures. Non-spontaneous at all temperatures. Then I'll be taking the reverse condition here, and now I'm not going to write down every time delta H negative. That means what? Delta H less than 0. Delta H positive means delta H greater than 0. You must be able to understand that, okay? Delta G is equal to delta H minus T delta S now. This is negative, this one is positive. Will I be able to get this as minus delta H minus T delta S? See, the thing is, do not think whatever are the 4 cases, we are dealing with different equation. No, equation is same. Equation is delta G is equal to delta H minus T delta S. According to the condition which we are having, we are modifying it so that we can derive the important conclusion. But you should not think that 4 varieties of different equation. No, the equation, underlying equation remains same. Now here, whatever is the temperature you take, every time your delta G is going to be negative. That means, can I say that this is going to be spontaneous at all temperature? So I'll be writing this as negative and this is going to be spontaneous at all temperatures. Finish writing this. After that, we'll proceed for the next one, next condition. Now the next thing is, if at all I take both positive, then there are two possibilities actually. Delta G could be positive, delta G could be negative. Now here we are having delta G is equal to delta H minus T delta S. This one is positive, this one is also positive. So positive negative multiplied means ultimately format of the equation remains same. Now if I take higher temperature, then T delta S product will be more in comparison to delta H. So entire delta G will become negative. So I'll say that delta G negative means it is spontaneous. But when? But at higher temperature. Getting it? So I'll be writing this as spontaneous at high temperature. I hope you got it. Then, if at all I say that basically temperature is low. If temperature is low, in that case the product of T delta S will be low and delta H will be more in comparison to it. If delta H is more and the overall will be delta G becomes positive, that means it is becoming non-spontaneous at lower temperature, right? So I'll be able to write down this as non-spontaneous at low temperature. Write this out, then we'll proceed further. Now let us say I am taking both of them negative. In that case also delta G could have two conditions here, positive and negative. Now here delta G is equal to delta H minus T delta S. Delta H is negative, delta S is negative. Ultimately I'll be getting minus delta H plus T delta S. Now if I take higher temperature means T delta S will be more in comparison to minus delta H. Delta G will become positive. If delta G is becoming positive, that means it is non-spontaneous. So I'll be able to write down this as non-spontaneous at high temperature, just the reverse of what we are learning in the third case, what we have learned in the third case. Similarly, if temperature is low, then this product will be lesser and minus delta H value is going to dominate. So delta G will become negative. So I'll say that it is becoming spontaneous at lower temperature. So I'll be able to write down this is spontaneous at low temperature. Right? So directly from this table they can ask you actually, like a very theoretical question, they may ask you identify the set of conditions under which a given reaction or process is spontaneous under all temperature, maybe non-spontaneous under all temperature, or is spontaneous at lower temperature, non-spontaneous at higher temperature, or else anything they can ask you from this particular table. So you must be comfortable for the condition which are written over here. So that is the theoretical aspect of this table. Then we'll see one numerical also. Hopefully everybody has done writing this. Then we'll proceed to the next one. So let me give you one numerical here. Predict the temperature at which the given reaction will become spontaneous. So I'm writing the equation carbon in the graphite form plus O2 gas giving you CO2 gas given delta H is 180 kilojoule per mole, delta S is 180 joule per mole Kelvin. I'm giving you certain option also, 510 Kelvin, 910 Kelvin, 710 Kelvin, fourth one is 1110 Kelvin. Find it out and let me know. And only hint I'll give you is first find out the temperature at which equilibrium is there and accordingly you can decide, right? Okay, good. Yes, fourth option people are giving. Very good. So the thing is here, you must understand, yes, majority of you have solved, it's good. So the thing is, first of all, we know equation is delta G is equal to delta H minus T delta S. First of all, find out at what temperature equilibrium is existing. At equilibrium, delta G is 0. So delta H minus T delta S is 0. Temperature will be delta H upon delta S. Now be careful with the units there. I have given you in kilojoule delta H, right? Divided by this 180. So basically you are having here 1000 Kelvin. So 1000 Kelvin is the temperature at which equilibrium is existing, right? So the thing is here equilibrium is existing means these two values are equal, then only delta G is 0, right? It is something like this, 180 into 1000 I have given you these many joules, then 1000 into 180. So this is the, at this 1000 temperature, 1000 Kelvin, both of them are equal. So that's the reason delta G is 0. For a spontaneous process, we want delta G to be negative. Negative in the sense, this temperature should be increasing beyond 1000, then only this particular value will dominate. It will become greater than the first one and delta G will be negative. So it's good that all of you have done it correctly, majority of you. So 1000, temperature greater than 1000 Kelvin. So the reaction will become spontaneous. So your answer should be fourth. Right, one more similar question I'll give you, but some other also aspect I'll add to this question, right? Identify or else let us say I change the language of the question for the given reaction or the process Br2 liquid getting converted into Br2 gas. Delta H is 31 kilojoule per mole and delta S is, let us say, 93 joule per mole Kelvin. Identify or else find two things. First one is temperature at which the process becomes spontaneous. And the second thing is you have to find out normal boiling point of Br2. Find it out, everyone. Good. Pawan has given correct answer. Is your name correct? Exactly Pawan Kalyan kya? Seems to be fan of Pawan Kalyan here, or else your parents are fan of him. So your parents are fan of him. Good. Are we done writing? Astrology, okay, fine. Nice name. Now the thing is here, same thing you had to do. Only thing is one extra added thing was there, right? Temperature greater than. Achha, Veermani sir also told the same. Okay, fine. Now the thing is, let us go for the solution part of it. We know delta G is equal to delta H minus T delta S. At equilibrium, delta G will be 0. So the temperature will be delta H upon delta S. I have given you 31 kilojoule and I have given you here 93. So this one will be 333.33, something like that. So it goes on. So I am simply writing 333 Kelvin. Now you must understand you are dealing with the phase change here, right? So phase change means liquid and gas will be at equilibrium, right? So at equilibrium, what is the temperature? 333 Kelvin. So this equilibrium temperature, what you are getting is actually the boiling point, right? And temperature greater than this 333 Kelvin, process will become spontaneous. Process will become spontaneous. Able to understand everyone? Now we shall proceed to the next part then, if at all you have got it. Now we are going to write down certain, kind of few points here and there, which are, kind of could be important here, and something related to Gibbs energy also. And we'll see what is free there, Gibbs free energy, right? Why do we say it is free, Gibbs free energy, right? Now first one is a very common point, or the energy profile diagram you must know. Basic energy profile diagram. On the x-axis, on the y-axis I'm taking energy. On x-axis, extent of reaction or the progress of reaction. That means how the reactants are getting converted into product. Now here, basically, I can show this as reactant and product, and basically this is what? Delta H, and this is positive because delta H is enthalpy of product minus enthalpy of reactant. Now the thing is, this is for endothermic reaction. Endothermic reaction. Similarly, we can plot a curve for energy and the extent of reaction here. So we can have a graph like this, where this is product, this is reactant, and this is actually your delta H. So delta H is negative here, and this is for exothermic reaction. Right? So for endothermic reaction, step up from the reactant side, and for the exothermic reaction, step down from the reactant side, right? Extent of reaction means how the reactants are getting converted into the product. Maybe extent of reaction, in place of that, they could also write down progress of reaction, one and the same thing here. Or the reaction coordinates they may write down. It means the same. First draw this, then we'll proceed to the next point here. Done. Now other point I am writing here is at equilibrium, G system is minimum and delta G equal to 0. This delta G equal to 0, so we have already understood, right? From the basically T delta S universe concept, we have already seen that. Now let us try to understand G system here. So let us say I am drawing a graph here between G system and basically your extent of reaction, that means how the reactant is getting converted into product. So the graph which is usually obtained is this one. This is for reactant, this is for product. And minimum, are you able to see there? So actually that is G system minimum, and this minimum is telling you that equilibrium has reached. Now what is the significance of this curve here? You might have heard for many reaction when you take reactant, maybe after the 20% conversion of the reactant into product, reaction does not happen further, right? Similarly, for some reaction, it could be 40% conversion of the reactant. After that, it is not getting converted into product, even though we are still having reactant and product in the same reaction vessel. So for some reaction, it could be 20% conversion. For some, it could be 50%, 55%, 60%, 70%, 90%, 99%. So it could vary from reaction to reaction, right? Now the thing is, let us say, take one example where you after 30% conversion of the reaction, your reaction is not going in the forward direction, right? So what is that indicating? After the conversion of 30% of the reactant into product, your reaction is no further, it is not further moving into product side. Reason being, equilibrium has been achieved, right? So any reaction, it happens in that direction where the reactant to product, or else where your G system is decreasing. It will keep on decreasing till the time it becomes minimum at equilibrium, right? Are we able to understand that? So after that, that means reactant to product, it was happening on its own. Spontaneously it was happening. Now once that G minimum has been achieved, if you still forcibly want to convert reactant into product, now you are not carrying out the reaction on its own. Some external agency help is required. And that is basically you are carrying out a non-spontaneous reaction. So for that reason, G system will increase. So beyond this equilibrium, you should consider that product can get converted into reactant, because the thing is, for product to reactant side, G system is decreasing. So simply you should understand this line very carefully, that they may ask you this thing actually in kind of statement based question. So you must know that at equilibrium, G system is minimum. It is becoming minimum and delta G is becoming 0, right? Hopefully everybody has drawn this graph. So I'll move towards the next portion, next note here. We know delta G is equal to delta G naught plus RT ln Q. Where what is delta G? This is change in Gibbs energy. And what about delta G naught? It is change in standard Gibbs energy. The thing is, standard means all the reactants and products, they are present in the standard state. And what about this Q? Q is reaction quotient. Let us say this is equation number 1. Now, basically, if at all I give you any reaction like A moles of A reacting with B moles of B to give you C moles of C. So reaction quotient you'll be writing like this: concentration of C, concentration of the product raised to the stoichiometric coefficient divided by concentration of the reactant raised to the stoichiometric coefficient. So I'll be writing A raised to A and B raised to B. But the thing is, this reaction quotient which you are writing, this is not for equilibrium condition, right? It is anything other than equilibrium. Now, if at all I say at equilibrium what happens? Delta G is 0 and Q will be replaced by the equilibrium constant. Let us say this is equilibrium constant and let us say this is condition number 2. So I am going to apply this condition into basically what? Into basically you will be getting, I am applying the second condition into the first equation here, right? That is correct. Equilibrium, at equilibrium always minimum. And Sai, I would appreciate, beta, if at all when I'm on that particular slide and you are having any doubt, you ask it then and there itself, because then it is kind of, it breaks the flow of any teacher. So please kind of, it's my humble request. If you're having any doubt, you ask there itself. Ma'am, there is the doubt there. I'll definitely sort it out. I'll explain you. Need not worry. But when already some other topic is going on and if you interrupt, So that means you are bringing the entire class also back to the question, back to your question, which is distracting the entire class. So please don't do that, okay? So when I am having delta G equal to 0, Q will be equal to K, which is equilibrium constant. So when I apply this into equation number 1, that is from 1 and 2, will I get delta G naught is equal to minus RT ln K. So let us say this is equation number 3. I hope it is clear up to now, whatever I have written on the board, okay? No problem. Is your doubt clear now or not? You can simply ask, no, ma'am, there is one doubt. Then I could have waited also, not an issue, okay? Is this clear up to whatever we have written here? Now the thing is, some important conclusion we'll draw from here also. If delta G naught is equal to 0, I say K will be equal to 1. The thing is, you can go for this. Let us say I'm writing this as 0, or else let us say I'm writing this as minus 2.303 RT log K, which is equal to 0. I have just simply converted this log to the base of E to the log to the base of 10, right? Now the thing is here, if at all I am equating this to 0, log K will eventually become equal to 0, and log K will be 0 when the value of K is 1, right? Log 1 is only 0, na? Right? So that's what I have written here. Understood this first conclusion which I am drawing here, delta G naught equal to 0 and K equal to 1. Similarly, if at all I say that delta G naught is less than 0, less than 0 means it is negative, negative will become positive, so ultimately I'll have K greater than 1, then only delta G naught will be less than 0. Let us try to analyze this first of all. When I say delta G naught is less than 0, it is negative. Negative gets cancelled out, so eventually log K has to be some positive value. So I'm going to write down that as log K should have some positive value. And that means if at all I place K equal to 1, it will become 0. If at all I place K value lesser than 1, so it will become negative. If I am placing K value greater than 1, then only log K will be positive. So let us take one value greater than 1. Let us say I am taking 10. So in that case, only log K value is what? That is basically positive. Are you able to understand? So K should be greater than 1 so that your log K value is greater than 1. Now if at all I place delta G naught greater than 0, if this is positive, log K has to be some negative value, and log K will be negative only if I am taking K value lesser than 1, right? Because if at all I take simplest example, 10 to the power of minus 1 with 0.1, it is lesser than 1. So when I place K value lesser than 1, in that case only am I getting minus 1 log 10, which is actually minus 1, right? So then only log K value is coming something negative. So hopefully everybody has understood this part, whatever I have written here. Got it? Then simply I can write down delta G naught is minus 2.303 RT log K, converting ln into log here. Is there any confusion to anyone in the condition 3 condition which I have written here? Is there any confusion to anyone? So I'll be able to write down log K as minus of delta G naught upon 2.303 RT. Now the thing is, I can very well write down one small note here, that if temperature is 298 Kelvin, R value is 8.314 joule per mole Kelvin. So I can have 1 upon 2.303 into 8.314 into 298. This value could be directly taken as 1.75 into 10 to the power of minus 4. So this can reduce your little bit of time for the calculation, right? If you remember it, well and good. If you do not remember, then also you can take approximation. You can write down 1 upon, this is 2.3, 8.314 as 25 by 3, 298, you can also take it as 300 Kelvin. You can easily get your answer. So whatever answer you'll be getting, the thing is that is not going to hamper any of the options so much. You can easily will be able to predict your closest answer. Please write this out. Then we are going to see one question based on this. Done. So let us see one question here. At 300 Kelvin, equilibrium concentration of A, B, C and D are 3 molar, 5 molar, 10 molar and 15 molar respectively. Find delta G naught in calorie per mole for the given reaction. So I'm writing down the equation. A plus B gives you C plus D. And you can very well take your 2.303 as 2.3 for solving. Please calculate it. And let me know the value. What is the answer? Is there any answer here? See, first for this one, you have to find out K value, which will be C into D upon A into B. So you are going to write down this as 10 into 15 upon 3 into 5. You will be getting K value as 10. Yes, Jonathan and Pawan, they have correctly given the answer. Good. So delta G naught is equal to minus 2.303 RT log K. And here I can approximately take this as minus 2.3. 2 calorie, this is 300 and log 10. So when you multiply this, you'll be getting minus 1380 calorie per mole. If at all you are taking exact value, then 1381.8 you should be getting, right? But as such, you can keep your answer like little bit of approximation, always you can apply, right? Now the thing is, here though I have given you simple question where kind of log K only you have to find out. Sometimes delta G naught might be given and you have to find out K value. So in that scenario, simple one I am telling you, not the interpolation part. Suppose after calculation you get log K value as 0.3, then what will be the value of K here? What will be the value of K here? You have to find out actually using anti-log. So whose ever anti-log you have to find out, you ask that number itself, whose log are you, right? So whose log is it? It is log of 2, right? So the thing is, you'll be having K is equal to 2. Then you take anti-log actually. Similarly, if at all you are getting log K is equal to 27. So basically, whose log is it? It is of 10 to the power of 27, log of this. So you'll be getting your value as K is equal to 10 to the power of 27. Are we able to identify? Getting it? And I'm not telling you about the interpolation part that will be dealt with in basically your ionic equilibrium portion. So we are done with 3 points here. Then let us write down delta G is a measure of maximum non-PV work. Non-PV work means maximum or else useful work. Useful work which can be obtained from a system at constant temperature and pressure. From a system at constant temperature and pressure. Right? Now the thing is, when I talk about PV work, just remember this as a statement. I'll explain you what I'm trying to say here. PV work means whenever I change the pressure, there is volume changes and vice versa, right? And when I talk about non-PV work, that means I'm not focusing on those pressure volume changes here. It is anything other than them, right? And it could be like lifting the pen against gravity, or else it could be like the work which is done by the battery there, which is, kind of to move the electrons there. And it could be like when you run or when you move, basically your muscles work for you. So actually that is also non-PV work. Now, what is the meaning of this statement? Let us say you are having delta G is equal to delta H minus T delta S, right? Now the thing is, let us take example of your scooty itself, scooty or motorbike, whatever it is. Now the thing is, you will be filling up their, kind of fuel, right? So let us say you have poured in petrol there, right? And you've taken 1 mole of it. And in petrol, let us say one of the component is octane, right? Now the thing is, you know that whenever you are filling up the petrol, on the combustion of that fuel, that is helping out to run your vehicle or else to move your vehicle. Now, suppose in that one such incident, 1 mole of whatever is the petrol which you have taken or the fuel which you have taken, when you do the combustion of it, it basically gives out 1000 kilojoule per mole of the energy. That means when you combust 1 mole of it in that internal combustion engine, it is giving you 1000 kilojoule of energy, right? Now the thing is, this entire 1000 kilojoule is not being utilized in moving your vehicle, first of all. The thing is, only some portion of this delta H is actually being utilized or else which is free for converting or for doing the useful work. That means which is for moving your vehicle. Are you able to understand? Not entire 1000 kilojoule is available or is free for doing useful work. And what is that useful work? Of moving your vehicle, right? Only some portion of it will be utilized for doing that useful work. Rest goes as heat losses. Now the thing is, you are having here, do you recall we have written delta S is equal to Q by T? So T delta S is equal to Q now. So rest is going as heat losses. Because whatever engines you are having, they are not 100% efficient, right? So the thing is, basically only some portion of the entire total enthalpy change which is there, only some part of it is getting utilized in doing the useful work there. Rest is going as heat losses. That's why people will be, kind of modifying the engines there. They are changing the design of it. They are changing the vehicle of the design, because all those aerodynamic portion also plays a role. It is not that vehicle is different. If you see that Activa is coming in different size and shape, you are having basically Jupiter also in different this one. Vespa, if you see, it is different model. So that doesn't mean that just for beautification of it, because the thing is actually automobile engineers take care of all those things there. That what design will be helping out in increasing the efficiency there, right? So are you able to understand this part? So simply remember, delta G is a measure of maximum non-PV work or maximum useful work which you can draw from any system at constant temperature and pressure. Now, let us go further here. So the thing is, as such, you are having basically, kind of important points about this is gone. or this is completed. Now one particular thing I told you that based upon Kirchhoff's equation, one question was pending, and hopefully do you people remember Kirchhoff's equation? While teaching you thermochemistry, I've taught you now. I've told you delta H2 minus delta H1 upon T2 minus T1 equal to delta Cp. That was the equation, if you remember, one of the Kirchhoff's equation. Now based on that only we are going to see one question here. So let us go for that. Find delta H for the reaction at 400 Kelvin. Reaction is Fe2O3 solid plus 3H2 gas, giving you twice of Fe solid plus 3H2 gas. Three H2O liquid here. Right? Given enthalpy change at 300 Kelvin is minus 20 kilojoule per mole. Cp values are also given here. So Cp for Fe2O3 solid is 100 joule per mole Kelvin. Cp for H2OL is 60 joule per mole Kelvin. Cp for Fe solid is 20 joule per mole Kelvin. Cp for H2 gas is 10 joule per mole Kelvin. Now here certain hint I will give you. T1 is 300 Kelvin. At this temperature delta H1 is given to you, which is minus 20 kilojoule per mole. At T2, which is 400 Kelvin, they have asked you to find out delta H2 value. And here you must understand one thing. Delta H2 minus delta H1 upon T2 minus T1, that is equal to delta Cp. This is only your Kirchhoff's equation. And here delta Cp you can easily find out the way you find out delta S actually. So delta Cp is summation of number of moles of product into Cp of product minus summation of number of moles of reactant and Cp of reactant. So using this you first find out delta Cp value. All of you find it out. No, Pawan, check your answer, beta. See, the thing is, you are having here 2 into Cp of Fe plus 3 into Cp of H2O minus Cp of Fe2O3 plus you are having Cp of H2. I have given you this as 20, this one as 60, this one is 100 plus 3 into 10. So you'll be getting this as 40 plus 180 minus 130. You should be getting 90 joule per mole Kelvin, not 190. Vishesha has already found out the answer. Good, very good. So the thing is, here again be careful with the units because delta H is given in kilojoule and here you are writing in joule. So I'll be able to write down this as 90 into 10 to the power of minus 3 kilojoule per mole Kelvin, right? So I'll be able to write down this as delta H2 minus of delta H1, which is minus 20, divided by 400 minus 300, that is equal to delta Cp value. Delta Cp is 90 into 10 to the power of minus 3. So it comes down to delta H2 plus 20. This is 90 into 100 from here into 10 to the power of minus 3, which will eventually become 9. So delta H2 will be 9 minus 20, which will become minus 11 kilojoule per mole. So that should be your answer. Delta H2 is this. Able to get this? Jonathan, some mistake you are doing, beta. Check it out, right? The thing is, you might have not seen this very properly. Minus 20, delta H1 is minus 20 kilojoule, right? So hopefully this is clear to all of you. So with this, actually we are winding up your thermodynamics chapter, and we'll be beginning with chemical equilibrium in the next class, right? So hopefully you have understood this, right? Please revise the things properly, right? And give your exam nicely. Thank you and have a nice day. QR code will be shared there, need not worry. Some of you are able to see that. I remember to see, I am sharing it with them. Please have your food properly and then you keep on studying. Hopefully now it is done. QR code people have scanned now.